Yes, we all ask it at some point. Maybe when we see a grandparent getting frail, maybe when we read about someone living to be 110. Is there a ceiling? Is there a number? Our bodies just can't get past. A final wall we all eventually hit. The question is simple. The answer is not. The oldest person who ever lived, with good records to back it up, was a French woman named Jeanne Calment. She lived to be 122 years and 164 days old. She was born in 1875. That was a year before the telephone was invented. When she died in 1997, the internet was already a thing. Her life spanned a world of unimaginable change. And for decades now, her record has stood. Nobody has beaten it. Nobody has even come that close. This is the first piece of evidence for a limit. If we keep getting better at medicine and nutrition and sanitation, you'd think we'd see the record creep up. But this record is different. It's a lonely peak. This has led many scientists to believe that maybe 122 or something around there is the absolute limit. Maybe around 125 years, our warranty just expires. They argue that our bodies are not designed for forever. They are designed to get us to an age where we can have children and maybe help raise them for a little while. Evolution doesn't really care what happens after that. So our bodies are built with a kind of planned obsolescence. Things just start to break down. And they don't just break down one at a time. They break down together. It's not like fixing a flat tire on a car. It's like the engine, the transmission, and the electrical system all failing at once. One of the big reasons for this is our cells. Our bodies are made of trillions of them. When we're young, these cells divide and make fresh copies of themselves to replace old or damaged ones. It's a constant process of renewal, but they can't do it forever. Think about the tips of your shoelaces. They have those little plastic caps called aglets. They stop the lace from unraveling. Your chromosomes, which hold all your genetic information inside your cells, have something similar. They're called telomeres. Every time a cell divides, the telomeres get a tiny bit shorter. It's like a countdown clock. Eventually, the telomeres get so short that the cell can't divide anymore without damaging its own DNA. So it stops. It just sits there. This is a state called cellular senescence. The cell becomes a kind of zombie. It's not dead, but it's not working properly either. And worse, these zombie cells don't just hang around doing nothing. They spew out a cocktail of inflammatory chemicals that can damage the healthy cells around them. As we get older, we accumulate more and more of these senescent cells. They contribute to arthritis, heart disease, and a lot of the other things we call getting old. It's like a neighborhood slowly filling up with grumpy, broken down houses that make the whole area worse. And then there's the DNA itself. Your DNA is the blueprint for everything in your body. It's constantly being attacked by sunlight, by chemicals in our food, just by the simple, messy process of being alive. Your cells have amazing repair kits. They are constantly patching up the damage. But they're not perfect. Over 100 years, little mistakes add up. A tiny spelling error here, a small smudge there. Eventually, the blueprint becomes so full of errors that the cell can't read it properly anymore. It starts building things wrong. This is what leads to cancer. It's what leads to organs failing. The instructions just get too garbled. It's like making a photocopy of a photocopy of a photocopy. The 1,000th copy is going to look pretty rough. Another problem is energy. Every cell has tiny power plants called mitochondria. They take the food we eat and the air we breathe and turn it into the energy that keeps us alive. But this process creates pollution, a type of molecule called a free radical. These are like tiny sparks flying off a fire. They bounce around inside the cell, damaging everything they touch, including the mitochondria themselves. Over time, our cellular power plants get rusty and inefficient. They produce less energy and more pollution. This is why older people have less energy. Their bodies are literally experiencing a power shortage at the cellular level. So you have these three things happening at once. The cells stop dividing. The DNA blueprint gets corrupted. The power plants fail, and they all feed into each other. It's a downward spiral. This is the biological argument for a hard limit. Our hardware just isn't built to last much longer than about 120 years. The systems are too complex. The chance of a critical failure somewhere becomes almost 100%. The data seems to back this up. While the average life expectancy has shot up in the last century because we've gotten good at curing diseases that kill young people, the maximum age hasn't really budged. We've gotten more people to the finish line, but we haven't moved the finish line itself. It seems stuck somewhere in the low 120s, but that's not the whole story. Not everyone agrees that there's a hard wall. They look at the evidence and see something different. They see a challenge, not a dead end. Their first point is simple. There is no law of physics that says a living thing must die after a certain time. Aging isn't like gravity, it's a biological process, and biological processes can be changed. They can be slowed down, paused, or even reversed. We see it in nature all the time. Look at the Greenland shark. It lives in the cold, dark waters of the North Atlantic. Scientists have found these sharks can live to be 400 years old, maybe even 500. They are the longest living vertebrate on Earth. They do it by living slow. Their metabolism is incredibly low. Their hearts beat once every 10 seconds. They grow less than a centimeter a year. They don't even reach sexual maturity until they're about 150 years old. Imagine that. They show us that a body with a spine, a heart, and a brain can last for centuries. Our basic body plan isn't a barrier. Or look at the bristlecone pine tree. Some of them have been alive for 5,000 years. They were seedlings when the pyramids were being built. They have incredible DNA repair mechanisms and ways to fight off disease and decay. They prove that life doesn't have to be a short burn. And then there's the most extreme example. A tiny creature called the immortal jellyfish. Its real name is Turritopsis dohrnii. When this jellyfish gets old or sick or stressed, it can do something incredible. It can revert back to its earliest stage of life, a little blob of cells called a polyp. It basically hits the reset button on its own aging. It then grows into a new jellyfish, genetically identical to the old one. It can do this over and over again. As far as we know, it can't die of old age, it can be eaten or killed, but it won't just wear out. This little jellyfish proves that biological immortality is possible. Nature has already figured it out. We just haven't. The argument is that human aging is a product of our specific evolutionary history. We evolved to survive in a tough world, to reproduce, and then get out of the way. Our biology reflects that, but what if we could change our biology? What if we could take the instruction manual for our bodies and rewrite a few chapters? This is where science is getting really interesting. For a long time, trying to stop aging was seen as quackery. Snake oil. But now it's a serious field of research. Scientists are not just trying to cure diseases like cancer or heart disease. They are trying to cure the underlying condition that causes them aging itself. One of the first clues came from a simple experiment. Take some lab mice and cut back their calories. Feed them about 30% less than they would normally eat, but make sure they still get all the nutrients they need. These mice live significantly longer, sometimes 30 or 40% longer. This caloric restriction seems to flip a switch in the body. It goes into a kind of survival mode. It starts recycling old parts more efficiently and protecting itself from damage. It's a process called autophagy, which means self-eating. The body starts cleaning house. This works in yeast, worms, flies, and monkeys. It seems to be a fundamental survival mechanism. Of course, it's very hard for humans to do, but it showed that lifespan isn't fixed. It can be stretched. Now, scientists are trying to find drugs that can do the same thing without the constant hunger. They want a pill that can trick the body into thinking it's starving, so it turns on those same protective pathways. One such drug is metformin. It's a common drug for type 2 diabetes, but researchers noticed that diabetics taking metformin seem to live longer, on average, than healthy people not taking it. That was a huge surprise. It seems to work by affecting the body's metabolism in a way that mimics some of the effects of caloric restriction. There are now major clinical trials underway to see if metformin can actually slow down the aging process in healthy people. Another is rapamycin. It was discovered in the soil of Easter Island. It's a powerful drug that suppresses the immune system, so it's used for organ transplant patients. But it also has a profound effect on a cellular pathway called mTOR. This pathway is a master regulator of cell growth. When you inhibit mTOR with rapamycin, it's like telling the cells to stop growing and start cleaning and repairing. In lab animals, rapamycin has been one of the most effective life-extending compounds ever found. The challenge is that it has side effects because it messes with the immune system. Researchers are trying to find ways to get the benefits without the risks. And what about those zombie cells, the senescent ones? There is a new class of drugs being developed called senolytics. Their only job is to seek out and destroy these senescent cells. In old mice, giving them senolytics works like a miracle. Their fur gets thicker. Their hearts work better. They can run farther on a treadmill. They are, in a sense, rejuvenated. Human trials are just beginning, but this is one of the most exciting areas of aging research. Instead of just slowing the damage, it's about actively removing some of the damage that has already been done. But the most radical ideas go beyond pills. They involve changing our genetics. The rise of gene editing technology like CRISPR has opened a door that was once pure science fiction. What if we could edit our own genes to be more like those of a long-lived animal? Could we give ourselves better DNA repair kits? Could we strengthen our telomeres? There's even a field called cellular reprogramming. In 2006, a Japanese scientist named Shinya Yamanaka discovered that he could take a regular adult cell, like a skin cell, and add just 4 specific genes to it. These genes, now called Yamanaka factors, could turn back the clock on the cell. They could erase all its history and turn it back into a stem cell, the kind of blank slate cell you have as an embryo. This was a revolutionary discovery. It meant that a cell's age wasn't a one-way street. It could be reversed. Recently, scientists have started to wonder if they could do this inside a living animal, not turning cells all the way back to stem cells, because that can cause tumors, but just partially reprogramming them, winding the clock back a little bit, not all the way to zero. In one experiment, they took old mice with a premature aging disease and gave them short bursts of these Yamanaka factors. The mice were rejuvenated, their spines straightened, their organs worked better. They lived 30% longer. It was a stunning proof of concept. The idea of erasing the damage of age at a genetic level is no longer impossible to imagine. So we have 2 very different stories. One story from biology and statistics says there's a firm ceiling around 125. Our bodies are complex machines that wear out, and gene calment represents the absolute limit of that machine's design. The other story from the frontiers of science says there is no ceiling. Aging is a program that can be hacked. With the right tools, we can slow it, stop it, or even reverse it. Which story is true? The honest answer is, we don't know yet. We are living in the middle of the experiment. It's possible that both are true in a way. Maybe there's a natural limit of around 125 years given our current biology. But maybe that biology is not the only option. Maybe we are the first generation to have the tools to start changing that biology. Think of it like flight. For all of human history, there was a hard limit on how high a person could get. It was the height of the tallest tree or mountain. Gravity was a fundamental law. But then we invented hot air balloons and airplanes and rockets. We didn't repeal the law of gravity. We just found clever ways to work around it. Longevity research might be doing the same for the law of aging. But this raises a whole new set of questions. They are not scientific questions. They are human questions. If we could live to be 150 or 200 or even longer, should we? What would that do to society? Our entire world is built around a lifespan of about 80 years. We go to school for 20 years, work for 40, and retire for 20. What does a career look like in a 150-year life? Would you have one career for a century? Or would you have 5 different careers, going back to school at age 90 to retrain for something new? What about marriage and family? Till death do us part has a very different meaning if death is 130 years away. Would people stay with one partner for over a century? Would women have children at age 60 or 80? What would it be like to have great-great-great-great-grandparents who are still alive and active? The structure of the family would change completely. And what about resources? The planet is already struggling to support 8 billion people. What happens if people stop dying off at the rate they do now? Would we have massive overpopulation? Would we need to strictly limit how many children people could have? A world full of old people could be a world that stagnates, one that is resistant to new ideas and change. Youth drives innovation. What happens when youth extends to age 50? Then there's the biggest question of all inequality. These new therapies, especially the genetic ones, will be incredibly expensive at first. Will long life be a luxury only the rich can afford? We could end up with a world where the wealthy live to 150 in perfect health, while the poor still die at 70. It could create a new kind of biological class system, a future that looks more like a dystopian novel than a utopia. The gap between the haves and the have-nots would become a chasm. And finally, what would it do to the meaning of our lives? Part of what makes life precious is that it's finite. It gives us urgency, it makes us want to create, to love, to experience things. If you knew you had 200 years, would you still get up and do things with the same passion? Or would you procrastinate for decades? Would life become boring? An endless stretch of time to be filled? Perhaps the curse of immortality we see in myths and stories has a grain of truth in it. Maybe we need an end to make the middle matter. So when we ask if there's a maximum lifespan, we are really asking 2 questions. The first is a scientific one. Can we break past the apparent limit of 125? The evidence is leaning towards yes. Eventually, we probably can. It might not happen in 10 years or even 50, but the tools are being built. The second question is a philosophical one. Should we? That answer is far less clear. It forces us to think about what a good life really is. Is it about length or is it about depth? Most people would agree that a long life filled with sickness and frailty is not what they want. The goal of this research isn't just about adding years to life. It's about adding life to years. The term for this is health span, the number of years you live in good health. Right now, for many people, the last decade of life is spent battling chronic illness. The real prize is not pushing the maximum lifespan from 122 to 142. It's making it so that someone can be as healthy and active at 90 as they were at 50. It's about compressing that period of sickness at the end of life into a very short time or eliminating it altogether. If we could achieve that, it would be a revolution. So, is there a maximum lifespan? For now, for a human living a natural life without radical intervention, the evidence suggests there is. It seems to be somewhere in the neighborhood of 125. We are biological machines, and like all machines, we wear out. But the future might be different. We are on the cusp of becoming the first species to be able to consciously rewrite its own biology. We are starting to understand the mechanisms of aging and how to manipulate them. The limit that has defined every human life for millennia might turn out to be just a temporary barrier, not a fundamental wall. The ultimate question will not be how long we can live, but how well we can live. And if we do manage to push back the darkness of death, we will need to be very wise about how we choose to live in that extra light. The challenges of a super long-lived society are just as daunting as the biological challenges of creating one. We might solve the problem of aging only to create a whole new set of problems about what it means to be human. The journey is just beginning.